In this video, we're going to talk about the chain rule, which is the last of our derivative rules. So we'll see what it says, how to use it, and we'll go through a few examples. We'll start off with sort of a silly situation here. Imagine we were throwing together a pizza party. We could talk about two functions here, C of P, which is the cost of buying P pizzas, and P of N, which is the number of pizzas we would need for a party with N people. And if we wanted to know how much it costs to throw the party, we would need to know kind of both of these functions put together. You'll see here I've drawn sort of a tower of dependence. And well, the reason I call it that is at the top we have C of P, which depends on P of N. That is, as P changes, as the number of pizza changes, the cost changes. And in turn, P depends on N. The price, the number of pizzas changes as the number of people changes. So there are actually three derivatives we could talk about, three rates of change. We could talk about how the cost changes as the number of pizzas change. That would be the derivatives dc dp. And maybe that's $9 per pizza. For each pizza we add $9 to the bill. We could talk about the rate of change dp dn, that is how the number of pizzas changes as the number of people changes. Maybe that's 1/3, which is a way to say we need 1/3 of a pizza for each person who comes to our party, or one pizza for every three people. But then the third rate of change could be how the very top of the tower depends on the very bottom, because ultimately C does depend on N. So how does the cost change as the number of people changes? And to sort of track this rate of change, this dependence, down the tower, or down the chain of dependence, we use what's called the chain rule. So this is actually one version of the chain rule that I've written here. It's not the one you'll find in the book. But dc dn is the product of these two derivatives going down the chain. So dc dp, dp dn, which maybe hypothetically are $9 and 1/3. So we put them together, and you can see the units sort of match up. And dc dn, the rate of change in the cost versus the number of people, is maybe $3 per person. So yes, this is a very cheap pizza party. Maybe we're ordering from Domino's. Okay, so again, that was silly, but let's see how we can do, I don't know, a more abstract question that we might see more often in calculus. Consider this function y equals the quantity x squared minus 2x all to the 99th power. And if we want to know the value of y prime, or the function y prime, its derivative, none of the rules we know yet can do that for us. Well, that's not true. We could use the product rule over and over and over, but that would get very, very tedious. So we'll do something similar to what we did in the pizza example. Notice here that the function y depends on this quantity x squared minus 2x. If we know that, we can raise it to the 99th power. We're done. So y depends on x squared minus 2x, but in turn, that quantity, x squared minus 2x, depends on the value of x. So this sort of intermediate function, x squared minus 2x, let's give it a name. We'll call it u. So just like in the last example, we can build a tower of dependence, a chain of dependence, if you will. So our function y, we could write it as a function of u, and it's just u to the 99th power. And that depends on u which we've defined to be x squared minus x, which of course depends on x. So y ultimately depends on x, but we've got this intermediate function in between. And we can talk about the rates of change for each step of this change, of the chain. And hopefully you can do these really easily. We only need to use the power rule and some of our very basic derivative shortcuts. dy du is 99u to the 98th power, and du dx, 2x minus 2. So the chain rule tells us how to put together these two dependencies. And if we want to know dy dx, how the top of the chain depends on the very bottom of the chain, we can multiply these two sort of intermediate rates of change. So dy du times du dx, and we'll put in the two rates of change we found, 99u to the 98th power and 2x minus 2. We're multiplying these, but it's helpful to have our answer completely in terms of x. And remember, we gave a name u to the function 2x minus 2. So let's unsubstitute. We'll plug in 2x minus 2 back in, and we'll get this as our derivative, dy dx. So that this is the rate of change in y as x changes. Stick around for the next video. We'll see the version of the chain rule that shows up in the book, and we'll try some examples.